in this lecture we shall be talking about some basic pipelining concepts. Now, you may wonder why we are discussing pipeline in the context of floating point arithmetic and floating point means hardware implementation of arithmetic functions. Now, you see what I would like to tell you here is that pipelining is a very commonly used and widely used technique to enhance the performance of a system without significantly investing in the hardware. You see, if I want to make something faster, I can always replicate some functional units. So, instead of one adder, I can use 5 adders. So, my addition time will speed up 5 times, right. But here the philosophy is different. We are not replicating hardware, we are using a different kind of a philosophy by which we can promote something called overlapped execution, whereby the performance improvement can be quite close to that what we can achieve by actually replicating the hardware. So, we are getting good return of investment without making any significant, you can say, enhancement in the hardware. So, this is the basic concept of pipelining. The reason we are discussing pipelining here is that we shall later on see how we can use pipelining to improve the performance of our arithmetic circuits, which we have already seen and discussed. And later on we shall also see how we can enhance the performance of the processor, that is called instruction level pipelining, how instructions in the MIPS 32 data path can be executed faster by implementing a pipeline there. But before that, you will have to understand what is a pipelining, how it benefits the designer, and what kind of speed up you are expected to get. Okay. So, here in this lecture we shall be talking about the basic pipelining concepts. So, as I had said, pipelining is nothing but a mechanism for overlapped execution of several different computations. Several different computation means they are possibly carrying out some computation on several input data sets. So, the basic principle is that we try to divide our overall computation into a set of k sub computations. These sub computations are sometimes called stages. I shall be giving an illustration later. Now, as it said, if I do this, there is a very nominal increase in the cost of implementation. Again, I shall be illustrating it with a real life example, but we can achieve very significant speed up, which can be very close to k. This is really fantastic. We are not really investing in additional hardware, just whatever hardware we had, we are basically dividing the hardware into smaller functional sub blocks, and by doing that we get an architecture where we can equivalently get a speed up of up to the number which is equal to the number of sub functional units that we have divided our total or overall computations into. Okay. So, this kind of pipelining can be used in several different areas of computer design. For instruction execution, we shall see later that several instructions can be executed in some sequence, because you see, you have already seen earlier that when instruction is executed in a processor, basically there is a fetch and execute cycle. During fetch, you fetch an instruction, then you decode it. Depending on the type of instruction, you can do the appropriate actions or operations to complete the execution. Now, the idea is that when an instruction is being decoded and it is being executed, so why not fetch the next instruction and try to decode it at the same time. This is what I mean by overlapped execution. Okay. So, this is what is there for instruction pipelining. Similarly, for arithmetic computation, that we shall be seeing here, that how we can speed up arithmetic computations by implementing them in a pipeline. Similarly, for memory access also we shall see later again that we can use the concepts of pipelining to speed up accesses from consecutive locations in memory. Okay. Let us take a real life example, say of washing. Suppose we have a requirement where we need to wash clothes, dry them and iron them. Suppose I have a machine which can do washing, which can do drying, which can do ironing. So, there are 3 stages of the machine. So, I feed my clothes to the machine. So, the clothes will be moving through the 3 stages and then I can feed the next cloth or next set of clothes, whatever. Okay. So, let us assume that this whole thing takes a time t, capital T. So, assuming that I can feed one cloth at a time. So, if there are n clothes I need to do washing, drying and ironing, the total time will be n multiplied by t. Now, as an alternative, what we do, we are saying that we are not buying 3 such machines, but rather we are breaking the machine into 3 smaller parts. There will be one machine which can do only washing, there will be one machine which can do only drying and one machine which can do only ironing. Okay. So, roughly the total cost remains approximately equal to the total cost of the original machine, because the capability are the same, just we have made this W, D and R separate. And just assuming that they take equal time, let us assume that earlier it was taking a time of t, now each of these will be taking a time of t by 3, t by 3, t by 3. Now, we shall see later very shortly that if I do this, then for washing, drying and ironing n clothes, I need a time 2 plus n multiplied by t divided by 3. So, if n is large, you can ignore t, it is approximately n t divided by 3, which means I have got a speed up of approximately equal to 3, equal to the number of pieces I have broken my original machine into. This is the essential idea behind pipelining. Okay. I can get a significant speed up. Let us see. So, washing, drying, ironing. So, after washing is completed, I will be giving it to the dryer. After drying is completed, I shall giving it to the ironing. So, to start with, during the first time slot, let us say the time slots are all t by 3 each, the first cloth reaches the washer. So, it finishes washing at the end of this time slot. So, then this cloth 1 will be moving to D. So, what will happen in the next time slot? This cloth 1 will be moving to D, but now the washer will be idle. So, I can feed the second cloth to the washer. So, now the washer and dryer are working on 2 different cloths in an overlapped way, they are working together. So, at the end of this time slot, dryer has finished with cloth 1 and washer has finished with cloth 2. So, what will happen next? Cloth 1 will come here to the ironer, cloth 2 will come here and cloth 3, the next cloth will come to washer. Okay. So, now means see all these 3 machines are busy. W, D and R. Now, at the end of this time what will happen? Cloth 1 is done, cloth 1 will be taken out. At the next time cloth 2 will come here, cloth 3 will come here and next cloth will come. So, at the end of this time cloth 2 is here. So, cloth 2 will be ready, taken out. Next time cloth 3 will be taken out. So, now you see after this initial 2 periods of time that is required for this pipeline to be filled up, after that, after every time slot I am getting one output. That means one cloth is finishing and I can take them out. That is why I talked about the total time as 2 plus n into T by 3. Like you see, first cloth comes out T by 3, T by 3, T by 3 at the time 3 into T by 3. Second cloth comes into 4 into T by 3, cloth 2. Third cloth comes into 5 into T by 3. Similarly, nth cloth will come at 2 plus n into T by 3. This is how we got this expression, right. Okay. So, extending the concept means whatever we discussed so far to actually computer hardware to the processor designs. So, we can extend the same concept. Suppose for some computation we want to achieve a speed up of k. So, there are two alternatives I have with us. So, I can use k copies of the hardware. This will obviously give us a speed up of k, but the cost will also go up k times because we are replicating the hardware. Alternative 2 is the pipeline. We are splitting the computation into k number of stages. This will involve very nominal increase in cost, but potentially it can give you a speed up of k, right. But one thing is required which we ignored. You see, if you think of the washing example, washing, drying and ironing, see after one machine finishes and a cloth comes out of one machine and goes to the input of the other machine, I need some kind of a tray or a buffer in between. The cloth will be temporarily stored in that buffer before it can be fed to the next machine, because it may so happen that when the first machine has finished with, let us say, the washing, the dryer is still working on the previous one, it is a little left. So, it is still not free. So, only when it is free, then only the cloth can be given to the dryer. So, I need some kind of a buffering mechanism in between the stages. Okay. So, this is what we talk about here, need for buffering. So, for the washing example, as I said, we need a tray between the machine's washer and dryer and also dryer and ironer to keep the cloth temporarily before it is accepted by the next machine. Okay. So, in exactly the same way, whenever we want to implement pipeline in hardware, we need something similar to a buffer, which is nothing but a latch or a register between successive stages, because one stage finishes some calculation and tries to give it to the next stage, but maybe the next stage is still not finished. So, that value is temporarily kept in a latch, so that the next stage, whenever it is free, it can take it from the latch. Okay. So, this is the idea behind the so called hardware pipeline. So, I shall be showing a diagram. It looks like this. I am showing a schematic diagram of a k stage hardware pipeline. This is called a synchronous pipeline because there is a clock which is synchronizing the operation of all the stages. So, as you can see, there are k number of stages. So, each stage involves some computation S1, S2 to Sk, and also there is a latch. So, what does the latch do? the latch will temporarily store the result of the previous stage before the next stage is ready to accept it, and the clock will be generating an active signal periodically, and clock period will be large enough so that all these stages can finish their computation, and also it should take care of the delay of the latch. Okay, this we shall come a little later, that how the clock frequency or the clock period can be calculated. And these stages S1, S2, they are typically combinational circuits. So, whenever clock comes, the next active edge of the clock comes, the next data is fed to S1, the output of S1 goes to S2, S2 goes to S3 and so on. So, there is a shift which goes on whenever the clock signal appears. So, in synchronism with the clock, the pipeline shifts result from one stage to the other in a lockstep fashion. Okay. You can classify or categorize the pipeline processor based on various parameters like degree of overlap, depth of the pipelining, structure of the pipeline, and how we schedule the operations. So, let us very briefly look at these. Okay. So, how these classifications actually represent the categorization. So, when you talk of the degree of overlap, well, one extreme can be serial, which is a strictly non-pipelined implementation. The next operation can start only after the previous operation finishes. So, here I have shown it schematically like this. This is an operation, let us say, which takes 1, 2, 3, 4, 5 steps. So, only after the first operation is completed, only then the second operation can start. So, it is strictly sequential, no overlap. There can be partial overlap, as the second diagram shows. Let us say the first 3, when it is executing exclusively, but when the fourth and fifth steps are executed, the second operation can also overlap its first and second with it. So, there is partial overlap. So, partial overlap naturally results in a speed up, because earlier it was taking so much time, but now it is taking 2 time units less. Okay. But in the extreme case, you can have something called pipeline, as I said, where so there is no concept of partial overlap, there is almost complete overlap. When the first operation is finished with the first step, it moves to the second step, and the second operation can start with its first step. So, they are working first step of this and second step of this, second step of this and third step of this, third step and fourth step of this, they work in an overlap fashion. This is called fine grained overlapped execution. So, here naturally the time you see is much less. So, depending on the degree of overlap, you can classify how deep or how efficient your pipeline implementation is. Okay. So, ideally you should have something like this. Then comes the depth of the pipeline. Well, we shall see earlier, we have seen earlier, we mentioned that if there are k number of stages, then we can have a potential speed up to k. Then you can argue that why do not we then have a very large value of k, so that we can get a very large speed up. But there are some limitations to increase the value of k. We cannot break up a computation into smaller pieces beyond a limit. Okay. Beyond a limit, it does not make sense. Maybe the delay of the latch will be will become more than the delay of the computation. Okay. So, depth of the pipeline is an issue. So, you can either have a shallow pipeline with a few number of stages, say 1, 2, 3, 4 stages, they are overlapped, or you can have a deep pipeline, let us say 1, 2, 3, 4, 5, 6, 7, 8, 9 stages. So, if you have 9 stages, then potentially you can have a speed up of 9. So, depth of pipelining is also a design issue, but also it is very important to evaluate that you can increase the depth all right, but you must also see that in what way you can allow the computations to proceed so that you can have overlapped execution without any conflict. So, we shall be seeing later that conflicts in a pipeline is very important, and there are so many techniques to handle them, right. So, for a shallow pipelining, because we are making the number of stages smaller, so individual stages are more complex, but if I have a very large number of stages, each stages will become simpler, individual stages will become simpler. Okay. Fine. Next comes structure of the pipeline. Well, we can have a linear pipeline which is most conventional. Linear pipeline means I have divided the computation into a number of stages which are supposed to be executed linearly one after the other. That means there is some kind of a straight line sequence. For every data input, first A, then B, then C, and then you take out the result. This is the order of execution for every input data. But for a non-linear pipeline, see, for very complex pipeline implementation, you can have this kind of non-linear pipelining. What non-linear pipelining says is that the stages do not execute in this kind of a straight line or linear sequence. You see, this is a pipeline again with 3 stages A, B, C. Of course, I have not shown the latches are also there. These arrows indicate the connection between stages. Like you can see, from A there is a connection to B, from A you can also move a result to C, and also you can take a result out. From B you can go to C, from C either you can take a result out or you can move it back to B or you can move it back to A. Okay. And new data is coming always to A. So, here in this example a possible sequence can be this A, B, C, B, C, A, C. How? A, B, that means it first comes to A, then it comes to B, then it comes to C, then again it comes to B, again it comes to C, it comes to A, again it comes to C, again it comes to A, then it finishes. It is A, B, C, B, C, A, C, A. So, here you can have some other sequence also. You can have, for example, A, B, C, B, C, and then come out. That can be another sequence. Okay. So, this is so called non-linear pipeline, where the stages may not execute in a linear sequence, like as this example shows, a particular stage may execute more than once for a given data set. So, for a given data set you are having 1, 2, 3, 4, 5, 6, 7, 8 steps of execution, where A is executed 3 times, B is executed twice, C is executed also 3 times. Okay. Fine. The last classification depends on how we are scheduling the pipeline. It can be either static or it can be dynamic. Static means you have the pipeline stages, and in the previous example you have seen that either I can execute them linearly or I can execute them in some particular order, okay, by feedback, etc. Static says same sequence of pipeline stages are executed for all data sets. So, you can have non-linear pipelining all right, but the sequence of stages you are executing, that will always remain the same, that will not change with time, okay. That is static. So, if one data or instruction stall means that data is using A again, so that I cannot feed the new data. Stall means due to some ongoing computation, I have to stop the pipeline temporarily for one or more cycles, that is stall. So, here it says if I stall a particular data, then all the subsequent data sets also get stalled. But in contrast, we can have a dynamic pipeline where with time the pipeline can be reconfigured so that different sequence of pipeline stages can get executed. So, this allows feed forward and feedback connection, as the previous example showed. This is a feed forward connection and this is a feedback connection. Okay. So, one example of a dynamic pipeline I can give, we shall discuss it later, is that suppose we are able to design a pipeline which is able to carry out both floating point addition and multiplication. So, when you are doing addition, then certain sequence of stages will be executed. When you are doing multiplication, some other sequence of stages will be executed. This is an example of a dynamic pipeline scheduling. Okay. All right. So, reservation table is a very commonly used data structure that represents the utilization pattern of successive stages. Let us take a simple example. So, what I mean by that? Suppose I have a linear pipeline S1, S2, S3, S4. So, when a data comes, so in the first cycle it goes to S1, second cycle it goes to S2, third cycle to S3, fourth cycle, this should be S4, okay, fourth cycle to S4. So, you see reservation table represent exactly that. So, on one side I show the stages, other side I show the time steps. First time step we use S1, second time step we use S2, third time step S3, fourth time step S4. So, this is basically a space time diagram, this is space and this is time, that shows precedence relationship among the pipeline stages. So, x axis as you can see shows the time steps and y axis shows the stages. Number of columns here 4 indicates the total time required by the pipeline to evaluate the result. So, it is 4. So, the reservation table is like this. So, let us look at a more complex reservation table. So, here we look at that nonlinear pipeline example we showed earlier. So, for the same pipeline example, I am showing two possible reservation tables. Same pipeline, suppose I am using it in a dynamic way. So, one computation x is here, other computation y is here. So, what it shows? It says that for computation x, we need 8 steps. How? First time step S1, second time step S2, third time step S3, fourth time step again S2, that means from S3 again you go back to S2, fifth time step again S3, sixth time step S1, so from S3 you go back to S1, then again S3 you follow this path to S3, then again S1 and you are finished, you come out. And the y computation it is like this, first time step S1, then S3, so you follow this path straight away, then S2, then S3, then S1, S3, again S1, again S3, from here you come out. So, x comes out of here and y result comes out of here. Okay. So, for the reservation table, although all of these are not being shown in these examples, the first one is shown, multiple cross marks in a row. Multiple cross marks in a row means, for example, here it means that for this computation, the stage S1 will be used in time cycles 1, 6 and 8. Stage S2 will be used in time cycles 2 and 4. S3 will be used in 3, 5 and 7. So, multiple x's in a row means repeated use of the same stage in different time cycles. Sometimes you may need a stage for an elongated period of time. So, you can have 2 consecutive x's side by side, contiguous cross marks in a row. which will mean extended use of a stage over more than one cycles. Okay. Sometimes it may be required, you may need for a computation a stage is required for 2 cycles. So, there will be 2 x's side by side, and well, here again it is not shown in these examples. You can also have multiple check marks in a column. That means, in a particular time step you can have a check mark here as well as here, which means both S1 and S2 are working together on the same data set. So, multiple stages are used in parallel during a clock cycle. So, in general you can have all these characteristics in a reservation table. So, let us make a quick calculation how we can compute the speed up and efficiency of a pipeline. So, we define some notations. Tau is the clock period of the pipeline that we want to use, the clock. Ti denotes the time delay of the stage I circuits, circuitry in stage Si, and dl denote the delay of a latch. So, there are k number of stages S1, S2 to Sk. So, the delays will be T1, T2 to Tk. So, the maximum stage delay I am denoting as tau m, which is max of Ti. So, the minimum clock period that I must have should be satisfying this criteria. It must not be less than tau m plus dl, that means the maximum stage delay plus the delay of a latch. This tau must be at least equal to this, it can be greater of course, and pipeline frequency would be the reciprocal of this 1 by tau. So, f will represent the maximum throughput of the pipeline, that means in this rate the output results will be coming out of the pipeline. If of course you have a linear pipeline and you are expecting one result to come out every cycle, but for a nonlinear pipeline things will become more complex, as we will see later. You may not be generating a result every clock cycle. Okay, fine. So, the total time to process n data sets, how much? It will be this. How? There are k number of stages, you recall. So, k minus 1 into tau, tau is the clock period. This much time is required to fill the pipeline. So, this k minus 1 into tau, this time is required to fill the pipe, and once the pipe is full you get one result every clock, that means every tau. So, that is n tau, that is how this expression comes. Tk represents the total time in a k stage pipeline. Now, if I have a equivalent non-pipelined processor where I do not have pipelining, how much will my total stage? If I ignore the latch overheads of course, I can assume that tau was the time taken for one stage in the pipeline. So, for my original non-pipeline processor it will be k into tau, and there are n data, n into k tau. So, here of course I made an assumption, that all stage delays are equal and the latch overheads are ignored. But still this will help us to make a very fair comparison. Let us see how much improvement we are getting by pipelining. Speed up Sk we can define as T1 by Tk, nkt divided by this. So, tau cancels out, you get this. So, if you divide it by n, so in the numerator is only k. So, this is k by n, this is 1 by n, and n by this is 1. So, as n becomes very large, this k by n and 1 by n tends to 0. Okay. So, denominator becomes almost equal to 1 and in numerator you have k. So, speed up tends to k. So, this simple expression tells you that we can achieve a pipeline speed up of maximum k as n tends to infinity. And we can define a term called pipeline efficiency, which defines as how close the actual pipeline performance is to its ideal value. You see, the actual speed up is Sk, just as we had expressed. Sk is the actual speed up, and the ideal speed up is k, right. So, I can divide it by k. So, how close this fraction is to 1? If it is 1, which means I have got the ideal value, maximum efficiency, but in practice the denominator is greater than the numerator. So, efficiency is a little less than 1, okay. And the pipeline throughput you can define as number of operations completed per unit time, total number of operations divided by total time taken to compute k data item, n divided by this. This is throughput. So, this is just a graph I am showing. So, as you vary the number of tasks n, so along the x axis I am showing, and speed up I am computing for 3 cases, k equal to 4, k equal to 8 and k equal to 12. So, as you see, as the number n increases, the speed up also increases, but for a 4 stage pipelining it levels up to 4, it cannot cross 4. For 8 stages it levels to 8. For 12 stages it approaches 12. So, it can never cross 12. Okay. This is something you need to remember. And lastly, I talked about the clock period. So, I only talked about a couple of things, the time taken for the circuits inside a stage to compute plus the latch delay, but actually the clock period depends on a few other things. Let us very quickly talk about this. So, the minimum clock period must satisfy an expression like this, tau greater than equal to t skew plus jitter, t logic plus setup. That means total time for skew and jitter, total time for logic and setup. What does this mean? Skew means, you see, so when the clock signal is generated, the clock signal goes to all points in the pipeline latches. Because of unequal distance of the wires, the clocks may not reach all the latches at the same time. There will be a small time difference. This is called clock skew. Clock jitter means because of noises on the neighboring lines due to capacitive effects, the delay of a signal line can vary slightly from one time to other. Maybe for the same latch, the period of the first one was tau, for the next one it is a little less than tau, for the next one it will be a little greater than tau. There can be small variations. This is called jitter. Okay. So, skew is the maximum delay difference between the arrival of clock signal at the stage latches, and jitter denotes maximum delay difference between the arrival of clock signal at the same latch. So, designers always try to lay out the clock signal in such a way that skew and jitter is minimized, but still there will be a worst case value here. T logic is the logic delay, which is the maximum delay of the slowest stage in the pipeline, and setup time involves the delay of the latch actually. It says what is the minimum time a signal needs to be stable at the input of a latch before it can be captured. So, this is a more accurate expression that gives you some lower bound of the clock period that can be used. So, once you know these figures or have a very fair estimate of it, you can calculate with maximum what frequency and clock rate you can operate the pipeline. So, with this we come to the end of this lecture. If you recall what we saw in this lecture, we have basically tried to convince you that pipelining is a concept where you can have significant benefit, significant speed up without making a significant investment. Okay. In our next lectures, what we will see is that there are some complexities in the pipeline. For example, for nonlinear pipeline, you can see that you may be using the same stage more than once for the same data. So, you are not allowed to feed the input data at every clock. If you do it, there can be some conflicts or clashes in some stages. Okay. So, something called pipeline scheduling to decide when I need to feed my next data is very important. So, we shall be looking into the pipeline scheduling aspects, and then we shall be seeing how some of the arithmetic operations, in particular the floating point operations, can be implemented in a pipeline. Okay. So, for this lecture we stop now. We shall be discussing some more issues of this reservation table scheduling in our next lecture. Thank you.